Hello, hello! Welcome everyone to the stream. Is my webcam working? There I am. Am I in sync? It looks pretty much in sync. Welcome to the stream. I am David Snopek from Snopek Games. This is our 21st stream, if you can believe it. I can see we've got a couple of eyeballs going. Of course, I don't know who is watching unless you say a comment, and then everyone else will also know who is watching, because you'll get a little character that bounces around the screen. I was a little worried last time that people were going to find the thing with the guys bouncing around the screen like annoying, because someone had made a comment to that effect on the previous stream, but no one said anything at all. So if you have strong feelings about the overlay, oh, now it's covering me up too. Hang on, is that because of this? Yeah, okay, I get it now. Please let me know in a comment if the overlay bothers you. I'm going to try and get it going as an actual overlay, because it's still now just like a window on my screen. Give me a second here. Stream tools. And then I've got to go to OBS and hit this button. Did that work? I don't know. Well, let me know, guys, because I can't actually see the screen when I am doing the overlay thing. Let me know if it's working, or if you are seeing nothing. That would be very useful information. So, yeah, for anyone who is... Oh, wait, no. Before we get serious, I want to show you guys something which will probably only be interesting to me and Elliot, because I don't know if you guys are into retro game development as well as like modern game development with Godot. But, oops. I have been working for the last, like, 2 days, I think, on a new prototype for the Commander X16 8-bit dream computer. It uses the, oop, that just covered up the overlay. Let me get this in the right spot. Commander X16, this one. What is going on? Why can't I bring this window over? Jeez, computers. Computers. Someone say that the overlay's in front of you. I can't see the screen of the camera, just the overlay. Oh no. This is, oh, I know what's wrong. Hang on, I got this. I gotta make the background green. That's what I gotta do. What's the button for that? I created this app. I should know all the buttons, but I don't. There we go. Okay. Tell me now. Things looking good now? And let me try for the bajillionth time to get this Commander X16 thing to open up. Oop. There we go. Yay, it's working now. Thanks, Aknakos. So the idea is this is going to be like a little Mega Man kind of style game. I don't know. I'm feeling good about it for 2 days' work. You can see there's no collision detection yet, but I've been making this in 6502 assembly for the Commander X16. For those who are unfamiliar, the Commander X16 is supposed to be this like modern retro console, so making like a new, or not console, computer, making a new computer kind of a spiritual successor to the Commodore 64, using the 65 CO2 processor, which is just like a sort of slightly newer iteration to the processor that was in the original Commodore 64. Slightly newer, meaning it was like made in 1981. The 65 CO2 is also the same processor used in the NES and the Atari 2600 and the Atari Lynx and a bunch of other stuff. Anyway, having a lot of fun programming in assembly, but that's not why you're here today. You are here for some Godot game development. So, a quick review for those who haven't been on the stream before. What are we building? One of my games, Retro Tank Party, available on itch and Steam. It's a multiplayer online tank battle game. It uses very naive netcode. That works. It works good enough, right? But we've been working for the last several weeks, maybe 10 weeks, I'm not sure at this point, converting it to use rollback and prediction netcode, as popularized by competitive fighting games, the GGPO library, if you're familiar with that. And we have the netcode working pretty good, actually. Ooh, who's stuck at the bottom? Someone's character is like stuck way down there. But one of the things that you need for rollback and prediction to actually work is deterministic physics. You need to have it so that given the same state on two different computers with the exact same inputs, the exact same things will happen down to, the binary level, like the decimal place level. And the way that we are doing that is we are making a new physics engine, which uses fixed point math. The Godot core physics engine, both the Godot custom one and Bullet, are not deterministic in this way. They're deterministic enough that we're able to kind of develop and test that netcode. But now we are trying to make, our own physics engine to finally solve that problem. Is anyone going to knock my little character out of the right side of the screen here? This is crazy. I've just been going up and down. And also for anyone else who is new, the little characters moving around on the screen is a Godot app that we made on stream a few weeks ago. All right, let me take a look at what's going on in chat. Just say hello to everyone. Welcome to Aknakos and The Clean and Elliot. Elliot says, but it's written in 65 CO2 assembly, not Godot. It's crazy good. Yeah. I'm happy with it. I'm happy with it for 2 days worth of work. The thing is, I've been complaining for like weeks about how slow developing in C++ is, because we're building our physics engine in C++. Developing in assembly is so much slower. Like, I spent, I don't know, 4 or 5 hours making him jump, just working on the jump. But actually, in common with our physics engine, that prototype and most of my prototypes for the Commander X16 use fixed point math. So it's another use case for fixed point math as we have been working on together on stream. So what have I done since last time? Well, last time we were working on, can I close this window? Will that kill the stream tools? I'm just gonna leave this window open. We were working on implementing a move and slide method for our physics engine to replace the Godot core one, so that we could then implement our own version of move and slide, which uses move and collide. And we got move and collide basically working last time, which was awesome. Then over the weekend, I spent a ton more time working on it, and I got move and slide working, which I'm going to show you in a moment, as soon as we get through the building and launching of our custom patched Godot here. All right, so you can see I run into it and I slide along it. Ooh, I got kind of stuck on the corner there. That was interesting. And I don't know if you can tell over the stream, but there is a little bit of jitter, which is sort of like vibrating on this side. I think it's just a tuning thing. Oh, and there's an invisible circle over here, so that's what I'm crashing into over here. I didn't put a visual representation for this circle collision shape. It's just a invisible thing hanging out there. So I think the jitter can just be solved with some tuning. The fundamental problem there is, okay, so the objects collide, right? So one is overlapping the other, and then you move it out so that they're not overlapping. How far do you move it out, right? If you move it exactly even when you push it out of the other object, it still kind of overlaps, right? Because the way that the collision code is written is that if one shape is exactly on the line of another shape, that's counting as overlapping. So then how far do you move it past the other shape? Do you move it like the smallest unit that we're able to represent with our fixed point math, just like 1/65,536th? And I tried that, and it works for completely oriented objects, but with a little rotation, there's actually enough fuzziness in the math that they could still overlap, right? So you can't just move it the tiniest unit. So it's like, well, should I move it 1 pixel out? Well, then like this really noticeable vibrating going on there. And so I think I have it right now moving 1/2 of a pixel. And so we're still getting a little bit of vibrating on the sliding. But I think we could play around with those values and make that actually work. So we have a working move and slide. There were a couple of really interesting problems that I had to solve when doing that. The first was when we implemented our move and collide, we just had it returning a bool saying there was a collision or no, there wasn't a collision. And what we really needed to implement move and slide is also the collision normal. That is a normalized vector pointing away from the point where the collision happened, and the remaining vector that you didn't move. So you're moving one object into another object, it says, oh, there's a collision there, and it moves it back out, the amount of distance that you didn't travel. So there's two things. The collision normal and the remaining distance that you didn't travel are necessary to implement move and slide. You can see here's the implementation for move and slide. It is so simple. It's just this code right here. Is this mine one? Yeah, this is mine. I was like, am I looking at the Godot one or my one? No, the Godot one is much longer. So basically, we have this max slides, which I think defaults to 4 or 6 or something, some small number. And we try to move and collide. It returns this collision. This is, it doesn't look like a return value, but it's passing it by reference, a very C++ way of getting multiple return values, because we still want the bool to tell us, did we collide or did we not collide? But then we want this extra information about the collision. And okay, so we didn't collide. If that happened, then we break. We don't need to do anything. We moved. There was nothing in our way. We're cool. But if we did collide with something, we calculate a new motion vector based on the remaining movement vector slid by the collision normal, right? And so long as the motion isn't nothing, in which case we also break, we just keep doing this until we find a good place to rest. And so the first challenge here that I was working on over the weekend was calculating that collision normal, and that like broke my mind. I got to tell you, I am really starting to get as sick of doing trigonometry. Let's go back to network stuff where I don't have to deal with so much trig. But I did eventually find a way to do it. Really quickly, I'll describe how the algorithm works. So this is a picture I drew last time talking about how our move and collide was going to find the two positions that we need, the high and low position, the high position being the smallest amount that we have to move forward to cause a collision. And from there, we derive all of our collision data, including the collision normal, based on that collision. So like if there were two shapes that we collided with, like, maybe there was another shape in here, and we only collided with the second, collided? We only collided with the second one by moving further. We don't want the collision information from that. We want the collision information from the first shape that we hit, right? So that's why we're getting this high value. And then this low value is like the furthest distance we can move without going into the other object. So that was our kinematic motion from last time. So calculating this collision vector, let me draw a new little picture. No, I don't want color. I want a blank. Give me a blank thing. Create. Okay. So to calculate the collision vector, let's draw a little collision here. We'll say this one collides with, I don't know, this one. We first calculate a separation vector. Oh, there's a lot of vectors. So many vectors. And the separation vector is the smallest distance that you would have to move one of the objects to move it outside of the other object. So basically, we're testing each face, right? So we're testing each face and seeing, does it collide? And we're able to say, like, well, along the axis of this face, we're colliding by a certain amount. And we take all of those amounts and find the smallest one, and that will yield us, I think in this case, the separation vector would be right here, possibly. I'm not a computer. I can't know this for certain, but that would be the smallest distance that we would need to separate these two objects, which means that this is the face on which we collided, and normalizing that separation vector is the normal vector. And it gets real sticky. Like it's easy to sort of logic your way through this, like if the collision looked like that. Because like, well, obviously it's colliding either on this face or this face, right? So, assuming this is the object that's moving, the collision normal would be a normalized, well, the separation vector would be this, and then normalize that to get the collision normal. But like when you collide on an edge, like that's kind of weird, right? So this is the object that's moving, right, into this object that's stationary. And so normally when you think of a collision normal, you think of colliding on one of the objects you're hitting's faces. So like you would think like, oh, either this normal or this normal. But in fact, what you want is the face from the moving object, but just with the vector pointed this way. So I don't know. It was maddening. I'm sitting here like wishing I was back in like a high school trigonometry class, because it's just been so long since I've had to think this hard about trig. But I did get that working. And there were a couple of interesting challenges related to fixed point math. If you remember from last time, we were talking about how getting the length of a vector in fixed point was unreliable because the length of a vector is basically the Pythagorean theorem, a squared plus b squared equals c squared. And since we're using these fixed point numbers, where we're basically multiplying every number by 65,536, these are very big numbers. And you take a very big number, square it, add it to another very big number that's also squared, and you get a huge number that was actually overflowing a 32-bit signed integer. And so here, let me show you the code. I showed you guys last time that I'd made this like length 64 that was doing the length squared 64 that was calculating the squared length using 64-bit numbers. Internal, it's in here somewhere. Here we go, length squared 64. But I was worried that that would mean we wouldn't be able to calculate the actual length. But I ended up implementing like a custom 64-bit square root function. So we are now able to get the length in a normal 32-bit fixed point number because we are calculating the square length using 64-bit numbers. We are square rooting it using 64-bit algorithm here, and then the number will be small enough after square rooted to then fit back into our fixed point data type. And until I fixed that, like the math for all of this separation vector, collision vector stuff wasn't working. So that was one thing that I fixed. And another really interesting unexpected problem with the same thing, with the length of, or not the length, but with normalizing vectors. Where's our normalize method here? Normalize. Not the transform normalize, I want the vector normalize. Or is that in, oh, here we go. Okay, so with the way our fixed point math is working, if you were to take any value that was lower than 256 and square it, the result would be 0. And that threw me off for like, I don't know, way too long. I'm walking through the debugger like, how can you square this number and get 0? Well, it makes sense when you step through the math, because multiplying two fixed point numbers, you're basically you multiply them together, and then you have to shift the whole number backward by whatever the amount of fractional units you're using for the fixed point number. And so I was unable to normalize these vectors. I was getting a lot of 0, 0 vectors when I should have gotten a nice clean, straight vector, because we weren't able to square these. And so I ended up implementing it this way. Since when we're normalizing a vector, we don't care at all about the length of it. We don't care about its magnitude in the end, because once it's normalized, the length will be exactly 1. We're able to say like, well, if x or y is less than 256, we multiply it by 256, and then get the length with our new special length function, which is custom square root, and we're able to normalize these vectors. And you might be thinking like, well, why would you have so many vectors that have lengths less than 256 when in fixed point math 256 with the format that we're using is like really, really tiny. I was seeing vectors that were like y0 x 7 and 7 means that is 7 65,536ths of a pixel, right? And the reason is because of our kinematic motion algorithm. So back to like the way we were calculating this high and low, like the high value is necessarily like it's intersecting with the other object just barely, just a teensy weensy tiny bit, because we've done this binary search to find what is the least amount forward we can move to still intersect. So that's what was getting me all of these like super tiny numbers, where normally you'd think those kind of tiny numbers just wouldn't come up. Anyway, a lot of fun, interesting trigonometry and fixed point math problems. But what we have now is, hang on, I gotta reload the chat here. Make sure everything's good with you guys while I'm rattling on forever. So now that I'm doing the chat like over on my Chromebook here, if my Chromebook goes to sleep, it actually like disconnects me from the chat. That's really lame. Well, anyway. We now have a working move and slide, which is the biggest thing that we need from the physics engine in order to start actually using it. And so yeah, let's start trying to use it. Let me know, folks out there, if anything I was just flying through was unclear or not making sense, or if anyone has any questions or comments or whatever. I'm getting the feeling like I'm talking to my wall right now. But there's two things at least that we need to implement before we can actually start integrating this into RetroTank Party, but they're two very small things. One is a rotate and slide method. So I don't know if you noticed when I was doing in here that it's possible by like going in here and then rotating to put part of the body inside of the other body, and then as soon as we move, it'll sort of snap out of it, because the move and collide will say, hey, are you already colliding? Oh no, our whole algorithm doesn't work if you're already colliding, and so it'll check for collision and then just move the body by the separation vector to start out. But we don't want to overlap like that. When we turn, we want it to kind of push us out of the body straight away. So we want to implement this rotate and slide method. And the other thing we need is collision masks. So like, you know how in Godot you can say like, I have these different collision layers and this object collides with this one. We need that in order for RetroTank Party to work even in like a minimal way. But both of those things are super duper easy given what we have. The rotate and slide should just be remixing stuff that we already have with our move and slide, move and collide, and the collision masks. I mean, that's just adding some properties. I think the hardest part of that will be making sure that we get the right like widget in the editor. All right, what's everyone saying? Arburing, very cool. Thanks, man. Aknakos, your overview sounds like you're almost re-implementing Godot. I'm re-implementing the physics engine for sure. not as many features, but I mean, that's scarily what's happening. Aknakos, it's impressive, but unfortunate that you had to instead of using existing Godot functions. You know, the more that I'm working on this, the more that I'm thinking that it would be impossible to implement a like normal Godot physics engine that was deterministic. Not that like Godot core couldn't have made like the core one be deterministic, but in Godot 4, the idea is going to be that with GD extension, or whatever we're calling the GD native replacement, you can make new physics engines that just get swapped in there, and you can now use like the normal kinematic body 2D and collision shape and all of that, and have it just use like Bullet or Box 2D or whatever other physics engine. But I don't think that you could do that with a fixed point physics engine, because in order for the fixed point stuff to be truly deterministic, you have to do everything in fixed point. So that means all of your code in GD script that you're writing to move your stuff around needs to be in fixed point. That means the positions and sizes of all of your bodies and shapes need to be defined in fixed point, not in floating point and converted to fixed point, because that leads to the same problem with, you know, losing determinism from floating point numbers. So like, I think that this fixed point physics engine will always have to be like its own separate thing. You know, maybe if some people who are way more interested in physics and trigonometry want to come like contribute to the project, we could make it into more of a full-fledged like physics engine. But I think it's always going to have to provide its own set of you know, body nodes and its own set of shapes, and implement its own like vector and transform code and all of that, because as soon as you include a single floating point number, you lose determinism. So I don't know. I didn't think it was going to be this hard when I started. What does Aknako say? That's great. I didn't know Godot 4's version of GD Native allows for that low-level editing. Yeah, it'll allow you to add different rendering engines too. So if someone wanted to make like a DirectX renderer instead of having to do Vulkan or OpenGL, which will be included in the core of Godot, they could do that. Basically, anything that can be done in C++ with a module, the goal is for GD extension, or I think that's what the replacement for GD Native is called, to be able to do all of those same things. Do you think it's possible with enough effort to use the existing high-level physics engine but replace the low-level for the use cases you're making? No. So I'm not exactly sure what you mean by the high-level physics engine. So there's the nodes and stuff that you actually work with in GD script, and that's kind of the highest level. But below that, the actual physics engine, which is really sophisticated and has all these features and covers all of these edge cases. But I mean, it's just like full of floating point math. You'd have to replace that, and then once you replace that, like, I don't know, it's hard to even understand that code with how it's kind of like grown and evolved and been bug fixed over time. I think the way we're doing it kind of might be the only way to lead to this result, unfortunately. Maybe replace the physics server but keep the nodes. Yeah, so that is what like you would be able to do with a a GD extension, and we could put a physics server in there but keep the nodes. The problem is those nodes store their positions as floating point numbers. So if your code is saying move and slide and passes a floating point number in, determinism's already out the window. You would have to somehow pass in a fixed point number, and since the like high level abstraction, the nodes are all like their positions, their transform matrix, all of that is just like floating point numbers. You can't do that. And so like in our versions of the nodes, let me open up the editor with our hacked Godot here. I have to switch the launch JSON to run the editor rather than just directly going into our app here. Ognago says, okay, got it. The nodes assume a certain implementation too. Yeah, it like so like a node 2D in Godot just keeps its position as floating point numbers. And like it's actually keeping its position, scale, and rotation as a transform matrix, which is, essentially 3 vectors that are all floating point. That a rotation vector, you do like, again, this is going to show how much I'm not good at trig, but it's like you do like sine, cosine, and inverted cosine to like get the values for the rotation part of the matrix, and calculating that sine value is going to be system dependent. Like the sine library that exists on your Linux versus Windows versus Mac, it's going to use floating point instructions, which makes it specific on your processor. It just, yeah, I think for floating point math, you basically have to do what we're doing. It's like what I was going to show you when I originally was going to come in here is we have our, this is our, let me hover, SG kinematic body 2D node, which has, the normal transform stuff from node 2D, and these are all floating point numbers. But then we have our separate properties, which are fixed position, fixed scale, fixed rotation, which are all floating point numbers. And then in our code, we're taking, a rotation, which is a fixed point number, our velocity, which is a special fixed point vector, and we're doing math on it all in fixed point, and then passing it into our move and slide. But in earlier versions, we were like just directly changing the fixed position. You have to do like from top to bottom in fixed point math. Anyway, let's get down to work. Certainly let me know if you guys have any more thoughts or questions or anything. So what was the first thing we were going to do? We were going to implement a rotate and slide. How are we doing on time? Oh, not so bad. Not so bad, even though I feel like I've just been babbling the whole time. So that will be added to our SG kinematic body 2D. We will put it right next to our move and slide. And what do we want as the return value from a rotate and slide? So what's the return value from a move and slide? Oh, it's the resulting motion vector. I don't know, the separation vector would actually be a kind of nice return value. Maybe we don't need a return value. Let's just start with no return value, and later we'll see if we can. So we'll just make this